In the previous lesson, we learned about the basics of motion. In this lesson, we're going to learn about the next step up. What happens when motion changes? Or in other words, what happens when an object accelerates? At the very end of this lesson, we're going to learn that acceleration can mean three different things. But for most of this lesson, we're going to be talking about mathematically what is acceleration. In the same way that in the previous lesson, we learned mathematically what velocity or speed are. As we get started, let's consider a problem. Okay, so let's say we have two cars. One of them is waiting at a traffic light that just turns green, and immediately after the light turns green, the car starts to move forward and accelerate. Now, you know this isn't happening in Florida, because if this was in Florida, the car would sit at the light until the car behind him honked, and then he would move forward. But this car is going to start moving immediately when the traffic light turns green. At the exact same moment, in the lane right next to that car stopped at the light, a car moving at a constant speed passes that initial car. So the light turns green, one car is moving at a constant speed, that's this car, and then the other car at the traffic light, immediately as soon as that car passes, because the light turns green, that first car starts to accelerate. Let's consider the motion of these two cars, one of them moving at a constant speed and one of them accelerating. Now, as we consider their motion, we're going to consider it graphically and mathematically. So this graph will suffice for me to plot the motion of these two vehicles. Now, let's just consider the difference between these two plots here, because I have a plot already, right? I have that one-dimensional plot that shows the positions of the cars. But that plot doesn't tell us everything that we need to know. Notice that everything is in one dimension. It doesn't really tell me anything about time. Now, I'm going to tell you something about the timing of this. Between each point, the blue points and the green points, 1 second has gone by. So there's 1 second of time separating the points on the top and 1 second of time separating the points on the bottom. Notice that, especially at the beginning, the points on top are much further apart per second than the points on the bottom. But on the bottom, you see that those points are becoming further and further apart per second, and that's going to be useful to know. Now, we're going to take this one-dimensional number line plot, and we're going to take that time information that we have, knowing that there's 1 second between each set of points, and now we're going to plot it two-dimensionally. Let's plot the distance dimension, the x dimension, on the y-axis of our graph. We talked in the last lesson about why we do that, because it's the dependent variable. And then we'll plot the time data on the x-axis of our graph, our independent variable. And we will get plots that look like this. Here's the blue object. Does this look like a constant velocity distance time graph? And let's consider some data related to our blue car. Now, you see I have two tables here. One of the tables is just the position time data, and that I could have pulled from either the number line or the graph very, very simply. The other one is velocity time data. And that needs to be calculated because it's not graphed directly on either the number line or the graph, but it's pretty easy to figure out. We just use our equation that relates velocity to the slope of our position time graph. And then we just plug in our position time point data into this equation to calculate the velocities for each position and each time. So if I look at this, between 0 and 1 seconds, I can plug in that my car moved 15 meters. And that's a really easy equation to solve. I'm going to end up with 15 meters per second between 0 and 1 seconds. What about between 1 and 2 seconds? Well, I could plug in my point data there too. I went from 15 meters to 30 meters, so I'm going to plug in those values in the appropriate place. And then another 1 second went by, 15 meters per second. I can do that for the third second. Again, it's 45 meters minus 30 meters. That's my change in position. My change in time is 3 seconds minus 2 seconds, or 1 second, 15 meters per second. And now you've picked up on the pattern. Because this is a straight line on a position time graph, my velocity is going to be constant. It's a constant 15 meters per second. And I verified that by doing all the calculations here. So what about our green car? Well, let's go ahead and plot the positions of the green car on our position time graph. And you'll see that the shape of the graph is different than it was for the blue car. Something different is going on with our green car. So let's calculate the values related to our green car. Now notice my position time graph has different sorts of values than my position time graph did for the blue car. For the blue car, all of my positions were the same distance apart. So if I subtracted the previous distance from the current distance, I always got 15. Now the distances are changing, or the differences in distances are changing as the time progresses. That means that the car is moving at a different rate as time goes by. Let's calculate the velocities for each 1 second that goes by. Now, interestingly, what kind of velocity am I calculating here? Well, I can't say that this is constant velocity anymore because the velocity is changing. So the best I can do here is calculate the average velocity for each of these points. And keep in mind, the velocity of this car is constantly changing. It's not going to stay the same for an entire second. The best I can do, though, with the data that I'm given here, is to calculate the average velocity for each second. So the car isn't actually moving at the average velocity, but what we're doing is we're assuming that the car is moving at a constant speed to get from the point at the first time to the point at the second time. All right, let's go ahead and calculate this. So I'm going to use the same equation as before. Between time 0 and 1, the car moves from 0 meters to 1.9 meters. So I'm going to plug those points into my slope formula to find velocity. And I find that the velocity between point 0 and 1 is 1.9 meters per second. Let's see what it is between points 1 and 2. I go from 1.9 meters to 7.5 meters. So I'm going to plug those into the appropriate places to calculate the slope. It's 5.6 meters per second. I'll plug in the next set of data. There I went from 7.5 meters to 16.9 meters between the second and third second, so from 2 to 3 seconds. That's a 1 second time interval, right? And 9.4 meters traveled, that gives me 9.4 meters per second. Same thing for between 16.9 meters and 30 meters between 3 and 4 seconds. That gives me a velocity of 13.1 meters per second. And between the last set of points, I moved from 30 meters to 46.9 meters in 1 second. That's 16.9 meters per second. Now, do you catch any trends in the data? It's hard to do with data that's in decimal form like this, but maybe you can pick out what the trend is. At least you notice that the velocity, the speed, the amount of distance being covered by this object is increasing as time goes by. And again, that's acceleration. When we're changing the speed of our object is changing the way that it's moving. This car is speeding up over time. All right, take one last look at that distance time graph for now and the shapes of the two curves on it, because I'm going to replace that distance time graph with a velocity time graph. And now that we've calculated all these velocities, let's go ahead and plot the velocities for the blue car and the green car. What do you expect it's going to be for the blue car when I plot the velocities? Well, it's always 15, so it's just a constant velocity, a horizontal line at 15. What about the velocities for the green car? Now remember, the position time graph for the green car was parabolic. It started increasing slowly, and then the distance started increasing more and more quickly as the speed went up. What about the velocity if I graph it here? Well, actually it ends up being a straight increasing line. My velocity is increasing over time in a linear fashion, And if you remember, when we had distance increasing in a linear fashion, the slope meant something, and the same is going to be true for our velocity that's increasing linearly. Okay, one other thing I want to mention, just a technicality in this graph here. I don't know how important it is to mention this, but maybe it's something that you notice. Technically, I'm not graphing the velocity of the green car because I don't know what its exact velocity is at each point. All I know is what its average velocity was between 0 and 1 second, and then between 1 and 2 seconds. So it's important for me to just note at the top of this graph that this isn't really just a velocity time graph. When I'm graphing the green car's position, I'm graphing the average velocity. And we show that by showing a bar over the top of velocity. That means it's the average. We calculated it using our average velocity formula. If the velocity is constant, like it was for the blue car, I don't have to say it's average because I know that it's remaining at 15 meters per second the entire time. But for the green car, the velocity was constantly changing. It was constantly increasing. And we just assumed that between 0 and 1 seconds, we reported one velocity. Between 1 and 2 seconds, we reported one velocity. And that one velocity we reported was the average velocity. We didn't take into account that the velocity was continually changing. Okay, we'll move on to the next part of this, where we're going to once again be looking at a new variable. In this case, we're going to bring acceleration into the mix. What is acceleration? Acceleration is the rate at which velocity changes over time. Now we're going to talk about why it's velocity and not speed in a little bit, although you could say that something is accelerating if its speed is changing over time too. But that word velocity is relevant, and we'll get to that. First of all, let's bring in our equation for acceleration. Does this equation look familiar to you? This equation should look pretty similar to our velocity equation, which was the change in position over time. Acceleration is the change in velocity over the change in time. Notice once again that I'm dealing with points, but this time my points are coming from a velocity time graph, not a position time graph. And the thing that makes this a little bit more difficult to consider is a velocity time graph already is a step up above a position time graph. You can tell things about a position time graph from a velocity time graph. And now we're considering analyzing that velocity time graph to find the slope of a graph that already was derived from a previous graph. That's what makes acceleration a little bit more difficult to consider, but it really does help if you work on considering the relationship between acceleration and velocity, and also the relationship between velocity and position, all in layers like that. All right, the next thing we're going to do is remember that we're dealing with a slope here. This is the slope of the curve of the velocity time graph. And you'll notice that our equation is the same as for velocity with distance time. It's a rise over run equation. In this case, our y values are velocity values on the y-axis, and our x values are time values on the x-axis. All right, let's bring in our acceleration tables now. Since we have position timetables, velocity timetables, now we can fill in acceleration timetables. How are we going to calculate the accelerations for our objects? Well, let's start with the blue car moving at a constant speed. How are we going to calculate the accelerations here? Well, we're going to use our new equation for acceleration, change in velocity over change in time. And this is the slope form of it. So we're going to take our velocity now minus our initial velocity divided by the time now minus the initial time. What do you notice about what's going to happen with this blue car that's always traveling at 15 meters per second? On the top, we're always going to have 15 minus 15. The graph is horizontal, so our y value is not changing. The rise is always going to be 0. So it doesn't matter how much time elapses. in the denominator of this because the numerator is always 0. And that means that our acceleration is always going to calculate to be 0 for an object moving at a constant speed. But does that make sense that an object moving at a constant speed is not accelerating? It has 0 acceleration. All right, now what about the more interesting car that's actually accelerating? How are we going to calculate its acceleration? Same equation, same form, and this time we're going to plug in the points from our velocity time graph. Okay, before we calculated the velocities, we plugged in the points from the position time graph. Now we're going to use our velocity time graph, and let's plug in some of those points. So first of all, I'll plug in between 1 and 2 seconds. We went from 1.9 meters per second to 5.6 meters per second. Let's calculate the rise over run value for that, and it becomes 3.7 meters per second per second. Okay, what is the label for acceleration? It's meters per second per second. And does that make sense? We're changing our velocity. We're changing the number of meters per second, and we're seeing how many meters per second we gain every second. The way that that's written is meters per second squared, but it's much more useful for you to think about it and visualize it as meters per second per second. So just keep in mind, meters per second squared is meters per second every second. Let's take a look at our next acceleration value. Here I have 9.4 meters per second at the end, but I started at 5.6 meters per second at 2 seconds. So going from 2 seconds to 3 seconds and from 5.6 meters per second to 9.4 meters per second, that calculates out to 3.8 meters per second per second. The next points, 13.1 meters per second is what I'm moving at 4 seconds. 9.4 meters per second was what I was moving at 3 seconds. When I calculate the slope between those 2 points, I get 3.7 meters per second. And then if I calculate the slope between the last 2 points at 4 seconds and 5 seconds, 3.8 meters per second squared. And I'm guessing that this should probably be constant. And the reason that it's slightly not constant is just rounding error. The actual value of acceleration is probably like 3.75, and it's just alternately getting rounded up and down based on the types of data that's being plugged in and how it's rounding off. But does it make sense that if our velocity was increasing linearly, the acceleration must be constant? Our velocity is increasing at a constant rate, which makes it linear. The acceleration then must be a constant horizontal line. This is going to make a lot more sense when we graph it, so let's go ahead and do that. Here I have all 3 of my graphs that I made side by side so we can compare them. Again, let's go back and consider the blue car moving at a constant speed first. Notice if something is moving at a constant speed, it's going to have a linear plot on a position time graph. Its velocity is constant, so its velocity time graph is just going to show a constant horizontal line. It's always the same value regardless of the time. And then because there's no acceleration, that means that the acceleration time graph is always going to be 0, a horizontal line at 0. What about the car that was accelerating? Well, the distance time graph is parabolic. And why is that? Because it's increasing in speed, which means that as time goes by, it's going to cover distance faster and faster and faster. So that means that the curve is going to get steeper and steeper and steeper as time goes by. And that's what a parabola does. It gets steeper and steeper as it increases along the x-axis. Do keep in mind that parabolas can be upward facing and downward facing, concave up and concave down. In this case, our parabola is concave up, but some accelerations cause concave down parabolas as well. Keep in mind that the parabola can face the other direction, the same as it faces this direction. Also notice that this parabola starts with its vertex at 0. However, sometimes parabolas will have part of the downward slope and then start curving upward in the graph, Acceleration can cause an object to start moving one direction, stop, and then come back in the direction it came from, and then keep accelerating in that direction. So you'll see all sorts of shapes of parabolas. This is just a very basic shape here. Now, notice my velocity time graph. The velocity time graph showed that the velocity was constantly increasing. It's not constant like it was for the object moving at constant speed, but it's constantly increasing, which means that the slope is constant and it's a straight line, an increasing line. Now again, acceleration could cause the velocity to decrease. So if I have a different kind of acceleration than the kind that I have here, I could cause my velocity to get smaller over time, but it should still move in a straight line as long as I have constant acceleration. And then I just said constant acceleration. Let's look over at the acceleration time graph. Notice that I have a constant value for my acceleration. It's a horizontal line on this graph and it stays the same. Now in this case there's a tiny bit of fluctuation because of rounding error, but you can see very clearly there's a horizontal line at around 3.7, 3.8, probably 3.75. Okay, so this was a real world problem we were considering with two cars meeting at a traffic light, but we didn't have real world data. This data was just made up to fit the patterns. Let's take a look at some actual real world data that we could collect related to acceleration. And actually we're going to look at two different cars moving. One of them is going to be moving at a constant speed on top, and the one on the bottom is going to be accelerating. Let's take a look at what those two different kinds of motion look like. Did you catch that? Let's watch it one more time. Notice the top car is moving at a constant speed. The bottom car is accelerating. And when I say it's accelerating, not only is it going faster, but it actually starts at a slower speed and finishes at a faster speed, and that's what acceleration is. The top car just moves at the same speed the entire time. Okay, now let's plug this in to Vernier video analysis and see what our video analysis results are. So I did video analysis on the top car and found that its position time graph was pretty linear. Was it perfectly linear? Well, no, this is real world data. So in the real world, even when something appears to be moving at a constant speed, there's going to be slight variations from constant speed. But you can eyeball this graph and say, you know what? Yes, this looks pretty linear. Now, when we find the velocity graph from our position time graph, in the real world, all of these little deviations from the line are going to be magnified when we calculate the velocity time and make a velocity time graph. Look at this graph. Does this look like a constant horizontal graph? All of the little aberrations in the first graph have been multiplied here. So there's error here. And not only is there error, but the car probably wasn't moving perfectly at a constant speed. There were probably some moments where the car was moving faster, some moments where the car was moving slower. It's just kind of close to a constant speed. So there's two things resulting in this graph looking like this. Number one, there is actual deviations away from constant speed. But number two, there's also error in the places that the points are placed on the car. They're not perfect, and both of those things contribute to this graph not looking very horizontal. Okay, now is it overall horizontal? Well, if you look at it, you see that there are just as many points above a horizontal as below, and we could place a horizontal in the middle there. So you can envision that this is very likely horizontal. It's just there's a lot of real world stuff getting in the way of showing it as a perfectly horizontal graph. And that's fine. This is what real world data looks like. And if you think that's bad, look at the acceleration graph. The acceleration graph deviates even further. If you look at the scale of the velocity time graph, notice that all the points fall between what may be an outlier point of like 1.25, so almost 1.5, and around 3. For our acceleration time graph, you'll notice that it's a much wider range. I have it scaled so it looks similar, but the range is from -10 to +10. So my data goes even further away, and again, that's just because I'm calculating a graph based on an already calculated graph. So all of those little aberrations in the original graph are magnified even more. But do you see how this essentially hovers around 0 meters per second squared? For every point that there is below 0 meters per second, there's pretty much a corresponding point that far above the 0 meters per second mark. So as a result, I can conclude that this is a zero acceleration over time. It's just that the aberrations in the graph are causing it to deviate away from that. All right, so maybe this is a bit of a stretch. You can collect better data than this with better objects that exemplify this a little better. Keep in mind that anytime you have an object as complex as a car, there's lots of moving parts. You have gasoline being burned in an engine that's causing the engine to turn a certain way. There's a transmission involved. There's all these moving parts that are going to cause the car to not move perfectly at a constant speed. And also we're using video analysis, which is the least precise, least accurate tool that introduces the most error, but it's our best way of analyzing this motion, so we do need to make sense of it even though it looks imperfect. Now, let's do the accelerating car next. Okay, so here's the data I collected on the car that was accelerating. You can see that once again there's a whole lot of aberrations, but the quadratic fit for the distance time graph is pretty good. It pretty much follows where this curve goes. You can imagine what the velocity time graph is going to look like. All of the little dips and bumps in the position time graph are now magnified in the velocity time graph. But you can see essentially there is a straight line that you can see is essentially increasing. And once again, for every point below the line, there's pretty much a corresponding point above the line that cancels it out. Now, if you look, you can see from the velocity time graph equation, you see the initial velocity of this car, right? That's the B value is the original velocity in our velocity acceleration time equation. It's just this is now written in its slope-intercept form. And we also know the acceleration from this equation because we see that the slope, 3.233, is the acceleration in a velocity time graph. So we have 3.233 meters per second being gained by this car, or 3.233 meters per second squared. All right, and then finally our acceleration time graph. Now this one is very difficult to pull any information from. This looks like it could be 0. But look at the scale on this. I have this going from -100 to 100. And if I zoom in, it just looks messy. You can't even really tell that it's horizontal. It goes up and down so much. So from this, it's very difficult to tell. Like, what if the acceleration was something like 2 or 4 or 8? It'd be very difficult to tell if this was far enough above the x-axis for it to average out to a value larger. And from our velocity time graph, we would expect our acceleration to be somewhere around 3. And 3 would be very difficult to decipher from this acceleration time graph. So we can at least see that the acceleration is constant, but it's difficult to tell from the graph what it is. All right, let's move on. And let's consider a problem based on this car's movement. Okay, so we're actually considering the movement of the car in the bottom video that was accelerating. A car speeds up from 4.6 meters per second to 8.5 meters per second. So we're going from about 10 miles per hour to about 20 miles per hour as that bottom car did in the video in 1.2 seconds. Assuming that the car accelerates at a constant rate, calculate the acceleration of the car during this time interval. Well, here, let's just look at this graphically again. Graphically, I'm going to have 2 points, right? One, and this is a velocity time graph, not a distance time graph, okay? On my velocity time graph, I have a point at 4.6 meters per second at 0 seconds, okay? So the actual coordinate would be 0, 4.6. And then another coordinate at 1.2, 8.5. And I'm being asked to find the speed, so what is the slope of the line that passes through those 2 points? I'm just going to use my equation in slope form here. 8.5 minus 4.6 over 1.2 minus 0, which calculates out to 3.9 meters per second divided by 1.2 seconds. So I gained 3.9 meters per second over 1.2 seconds. How many meters per second is that per second? Well, if I divide, I find that that's 3.25 meters per second squared. And if I were using significant figures here, I need to keep it to 2 sig figs, so it would be 3.3 meters per second squared. If this same car continues to accelerate for a total of 3.0 seconds from the start, so it's starting at 4.6 meters per second, right? And it's accelerating at the rate we just calculated, 3.3 meters per second squared. How fast will it be going after 3 seconds from the start? Well, now we're going to use the, either you want to call this the slope-intercept form, or more accurately, the point-slope form of this equation. And I'm just going to plug in all of my values. My original velocity is still 4.6. That's what I started at. Now I know my acceleration is 3.25 meters per second squared, and 3 seconds is my time interval. I'm going to calculate this out and find that I will be moving at 14.4 meters per second after 3 seconds if my constant acceleration continues at the same rate. All right, last few things to talk about here. I just want to mention that because we're dealing with velocity change, acceleration, like velocity, is a vector value. That means that not only does the size of the acceleration matter, but the direction of the acceleration matters. There are actually 3 ways to accelerate, okay? Acceleration occurs when an object speeds up. That's the one that we're used to talking about. When you say that something is accelerating, you think of it speeding up. But you could also say it's accelerating if it's slowing down. It's just that the value of the acceleration would be negative. In physics, we don't typically use the word deceleration. You'll hear it used sometimes just to emphasize that acceleration is negative. But acceleration can be used to talk about a negative acceleration or an object slowing down in physics too. So just because the word acceleration is used doesn't mean an object's speeding up. It could be negative and the object could be slowing down. And then lastly, acceleration also occurs when objects change direction. Because it's a vector value, anything that changes the velocity, including the direction that an object is moving, accelerates the object. Interestingly, you usually refer to the gas pedal in a car as the accelerator, but there's actually 3 accelerators in the car. You have your gas pedal, the brake pedal will cause an acceleration, and the steering wheel also causes acceleration. All right, and that's what you need to know about acceleration. Now you know about 2 different kinds of motion: constant speed motion and constant acceleration motion.